In this video, we're going to talk some more about improper integrals. So we're going to talk about our test for convergence and divergence. If we can't evaluate an improper integral directly, we first try to determine if the integral converges or diverges. If it diverges, that's the end of the story, we're done. If we can determine that the integral converges, then we can use numerical methods if we really need to know what the value of the integral is. For us, mostly we'll just be trying to determine does it converge or diverge. So an important tool in this is what's known as the comparison test. So I'm going to pull this up a little bit. So the comparison test says let f and g be continuous on an interval from a to positive infinity. So since f and g are both positive, then there's two things that we can do. So one thing to note is we're going to be going to infinity. So the comparison test can only be used on integrals where the upper limit is infinity. And then we're going to have this relationship between f and g. So normally we're going to try to we'll be given either f or g. One of those two will be the integral we're trying to actually determine if it converges or diverges. The other one is one we're going to pick to be the comparison function. So the first part says if f converges, f of x converges if we know that g converges. So f would be the one that we're really trying to determine. And so if we can say that f is less than a function that we know converges, then our function is going to converge as well. That is, if a function is less than a known convergent function, then that function must converge as well. The second thing says that if that we can claim that g diverges if we compare it to a known divergent integral. So if we're not sure about g, but we can see that f diverges and that our function g is bigger than a known divergent integral, then our integral must diverge as well. So that's the kind of essence of the comparison test. If we can show that the integral that we are not sure about, that we can't actually evaluate, if we can find a function that is smaller than that, that is bigger than that and does converge, then we can claim that our integral converges as well. If we can show that our integral is bigger than an integral that we know diverges, then we can claim that our integral diverges. And here again is our emphasis. We can only do this for integrals where the upper limit is positive infinity. So here is an example. Does the integral from 1 to infinity of e to the negative x squared converge? So this is not an integral that anybody can do because we can't integrate e to the negative x squared. So first we can note that e to the negative x squared, that's an exponential decay function, so it's going to be greater than 0 for all x. So we have satisfied that condition that the function has to be positive. So it's got to be greater than or equal to 0. Okay, now the next part is the really hard part, is how do you decide what to compare it to? So we want to compare it to an integral that we actually know how to do. So we might think about that in this case our e to the negative x squared is going to be something that's a decay function, but that e to the negative x, which is something we can actually do, is going to, it will not quite approach, it'll approach 0 not quite as fast as e to the negative x squared. That is, e to the negative x squared is equal to e to the negative x at x equals 1, which is our lower limit. And for every point after that, e to the negative x is going to be greater than or equal to e to the negative x squared. Does that make sense? So if you put in something like 2, then e to the negative x is going to be e to the negative 2. So for x equals 2, e to the negative x is going to be 1 over e squared, whereas e to the negative x squared is going to be 1 over e to the fourth. And so e to the fourth is bigger than e squared, therefore it is going to be 1 over e to the fourth will be less than 1 over e to the second. Okay, so now what we can do, since we have established that that the integrand e to the negative x is going to be greater than or equal to e to the negative x squared, if we can show that e to the negative x converges, the integral from 1 to infinity of e to the negative x converges, then our integral will be less than or equal to a known convergent integral, and by the comparison test, we can claim that our integral will converge as well. So we will do what we do, limit as b goes to infinity of integral from 1 to b of e to the negative x dx is going to be that limit as b goes to infinity of negative e to the negative b going from 1 to b, which is e to the negative b minus a negative e to the negative 1. And so as b goes to infinity, this is going to go to 0, and we will get e to the negative 1, or if you rather, 1 over e. Either way, this converges. So we can say then, by the comparison test, should probably capitalize that, test, the integral from 1 to infinity of e to the negative x squared dx converges. Okay? That's the idea. Now, that's the hard part. What challenges most people with the comparison test is that in order to use it, we first of all have to decide, does our integral actually converge or diverge? We have to kind of make a judgment call. If we decide it converges, then we got to figure out, well, what is an integral? What can we use as an integrand that is greater than or equal to our integrand that will converge? Or if we decide that it diverges, how can we find something that we know is less than that will diverge as an integral? And so to help us with that a little bit, we're going to talk about this integral of 1 over x to the p from 1 to infinity. So what happens with our power, the integral of a power function? So why is this improper? It's going to be improper because our upper limit is infinity. So this is going to be because the upper limit is infinity. We're going to learn in a little bit that there are other ways of getting improper integrals besides having infinite limits. But that's why, for now, that's why this one is improper. Now, if we choose p to be 1, then our integral is going to be the limit as b goes to infinity, integral going from 1 to b of 1 over x dx. So we know that's going to be the limit as b goes to infinity of the natural log, and we don't really have to use absolute value here because our interval is going from 1 to positive infinity, so there's no danger of us trying to evaluate a logarithm of a negative. So this is going to be the natural log of b minus the natural log of 1. Now we know that the natural log of 1 is 0, and as b goes to infinity, the natural log of b is also going to go to infinity. So even though it goes very, very slowly, remember a logarithm is a very slow growing function, it is going to diverge. So for p equal to 1. So this is going to help us down the road. Let's explore this a little bit more and say, why does this converge for p greater than 1? So imagine now that we're going to take this integral, again, b going to infinity of 1 over x to the p, and I'm going to imagine that it's just something barely bigger than 1, because I think this will help illustrate it. So this is, remember, going to be the integral of x to the negative 1.1 dx. So using our power rule for integration, we're going to add 1 to that integral and then do 1 over that new integral as our new constant. But the important thing here is that if p is bigger than 1, that this p plus 1, whatever that is still going to be a negative number. And so that is going to be this 1 over 1 minus 1.1, and it's going to be x to the, and this is going to be something negative. So that p minus 1 that we're going to get, or it'll actually be p plus 1, but the p here is a negative number bigger than 1, is going to be still a negative number. So as we go from 1 to b, when we plug in the b here, this, because you're going to have this 1 over 1 minus 1.1 times, that's going to be a 1 over x to the something, whatever that result is. And so that is going to go to 0 is the whole idea, which will make this then converge. So it's not going to blow up because you're going to have some residual x in the denominator. By the same token, it's going to diverge when this p is less than 1. So imagine now we're doing integral from 1 to b, limit as b goes to infinity of 1 over, and I'm going to just call it x to the 0.9 so we can make our point by seeing an actual value. So when this is going to be the integral then from 1 to b of x to the negative 0.9. So when we add 1 to that exponent, you can see that whatever that p is, that it's going to actually be the negative of p, that our result here is now going to be positive. And so because that is positive, when we plug in that b in there and let b go to infinity, that is going to go to infinity, which will make it diverge. Okay, so this is now what we want to take away from this is that we have kind of a boundary of sorts here, at least with power functions. So when we're looking at a function y equals 1 over x to the p, when p is equal to 1, we know that's going to look something like that. That is going to be a boundary. Anything for any values of p that are bigger than 1, so that means, remember, that exponent in the denominator is bigger than an x to the first, so 1 over x to the second, 1 over x to the third, 1 over x to the fifth, all of those are going to somehow approach the x-axis faster and fast enough that that area between the curve and the x-axis is going to be finite, and that means that that integral is going to converge. Any function where the p is less than 1, so imagine now you have like y equals 1 over the square root of x, y equals 1 over x to the 0.8, anything like that is going to somehow, when you come in here, oops, I lost my pen. As you come in here, it's going to lie above this curve y equals 1 over x, and so it's not going to approach the x-axis fast enough to capture a finite area. And in fact, what's going to happen then is it's going to diverge. So, how can this help us? When we are looking at an integral, And whatever that may be, if we can kind of say what's going to happen to this integrand, this function here, as x approaches infinity, is it going to act like some kind of power function 1 over x to the p? If it is, and if that thing that it's going to act like has an exponent that is greater than 1, we're going to suspect that it's going to converge, and we can try to find a comparison function that is going to be that 1 over x to the p that is going to converge. Similarly, if we see that it's going to act like something that is a power function with the p less than 1, we're going to suspect that it diverges, and we're going to look for a comparison function that is going to be 1 over x to the p with p smaller than 1. Let's do some examples and see how this might look. So, now, and I'm trying to really remind you, we can only use the comparison test when our integral has an upper limit of infinity, if it's improper because of the infinite upper limit. And we also need that our integrand is going to be non-negative, at least after some point in time. So here we look at this function and we can say, well, it's always going to be positive, so our f of x here is greater than or equal to 0 for x greater than or equal to 1, our lower limit. So it's going to meet that criteria. Now, what to do? We can't necessarily integrate. We can try to figure out a way to integrate it, but really what we want to do is see this is going to act like, as x goes to infinity, that plus 5 is going to be pretty insignificant. Our function is going to act like 1 over x to the third. Now 1 over x to the third is a power function where our p is greater than 1, and so an integral of 1 over x to the p with p greater than 1 is going to converge. So we suspect that our integral here is going to converge. So now what we want to do is come up with an integral that's going to be easier to evaluate than this, that we know is greater than or equal to this one. So we want to find a new comparison function that is going to be greater than or equal to 1 over x to the third plus 5. So if we can look for something that's going to be 1 over x to the p that's going to be greater than or equal to this. So remember, if our denominator is smaller than this denominator, then our fraction is going to be bigger than this fraction. So if we choose our comparison function to be 1 over x to the third, then that's going to be greater than or equal to 1 over x to the third plus 5, at least on the interval from 1 to infinity, which is what we're integrating over. So we can now do that. So we're going to take the limit as b goes to infinity of the integral from 1 to b of 1 over x to the third. If we can show this converges, then we can conclude that our original integral must converge as well by the comparison test. Well, we can do that because this is going to be the limit as b goes to infinity, integral from 1 to b of x to the negative 3. So that's going to be x to the negative 2. We'll get a negative 1/2. We're going to go from 1 to b and take that limit as b goes to infinity. So that's going to be negative 1 over 2b squared minus a negative 1 over 1, 2 times 1, so I guess a 2. So as the b goes to infinity, this is going to go to 0, which is going to be 1/2, which means it converges. So what we have shown is that our original integral is less than or equal to an integral that we know converges, Therefore, by the comparison test, our integral, that integral from 1 to infinity of dx over x to the third plus 5, converges as well. Hopefully that makes sense. So, as we look at our next one, and we see that, well, this is really hard to figure out and maybe tough to, and really hard to integrate, we can say, well, I know that as x gets really, really big, this sine x, which is going to always be between -1 and 1, is going to be at its biggest 1. So we know that this integral will be less than or equal to the integral from 1 to infinity of 3 plus 1, which is 4, over x. Well, that's going to be bigger than that, but I suspect this is going to act like 1 over x, and 1 over x is going to diverge because our p is equal to 1. That integral of 1 over x is going to give us a logarithm. So instead, what I want to do is not make it less than or equal to. I want to make it greater than or equal to an integral that I know diverges. So if I choose sine x to be its smallest, -1 plus 3, then I can say this is going to be, our integral is going to be greater than or equal to this integral. And I can show that this integral diverges. So I'm going to say the limit as b goes to infinity, and I'm going to call that 2 times the integral from 1 to b of 1 over x dx is going to be 2, I'm going to say the limit as b goes to infinity of 2 natural log of x going from 1 to b, which will be 2 natural log b minus 2 natural log 1. So that this we know is 0, and as b goes to infinity, this natural log of b is going to go to infinity, which means this integral is going to diverge. Therefore, by the comparison test, since we have just shown that our integral is greater than or equal to a known divergent integral, by the comparison test, the integral from 1 to infinity of 3 plus sine x all over x dx is going to diverge as well. Hopefully that makes sense. Okay. I think that's all I got for this one.